Today we're going to go into some detail about what Professor Chu talked about regarding material in Chapter 3, and then we're going to briefly go over Chapter 4. So we're going to talk about the time-independent Schrodinger equation, mostly in one dimensions, and then I'm going to quickly go over infinite square well and free particle, and I want to emphasize something here. And then I will show you how to solve the finite symmetric square well. Okay. And then we'll introduce the probability current and the expectation values of operators. So first of all, let me motivate the time-independent Schrodinger equation. Okay, this is the abbreviation. Why do we care about this? It's extremely important because let's think about the general dynamical problem posed in the Schrodinger equation. So I have some Schrodinger operator, a state that is a function of, I'm staying in one dimension right now, okay. X and t. Right. This is equal to its time evolution. Okay. So we can formally solve this solution. Supposing that we have a time-independent Hamiltonian, we can solve this as okay. So this is how you would solve any first-order differential equation in time. Okay. So now you see that we have exponentiated an operator. Now the special case, if I have some phi n, okay, such that it is an eigenfunction of the Hamiltonian, okay, then this time evolution problem simplifies a lot. Okay. So we can write plugging in the eigenvalues here. Okay. So you see that the temporal and spatial dependence of this wave function, they're decoupled for the eigenfunction. And we also know that we said the Hamiltonian operator is a Hermitian operator. This is important because now it has a set of eigenfunctions that are complete for the problem. So this allows us to expand any general wave function. Let's do this expansion at t equals to 0. Okay. So I can expand any general wave function in terms of the complete eigenfunction, a set of eigenfunctions. Okay. And this expansion coefficient is given by, in one dimension, it looks like this. Given by the overlap of these two functions. Okay. Well, you have no doubt seen this before. So now we can treat the general problem of time evolution by doing this expansion and plugging it into this equation. Okay. So we get that the general time evolution.
You might want to mention that the eigenfunctions are all normalized. That's why you see n is.
Oh yeah. So Hermitian operator doesn't just have complete eigenfunction basis, they're also all orthonormal. Okay.
You have to normalize them. They're
Yeah.
not all orthonormal.
Yeah, make sure you normalize your eigenfunctions. So that is the take-home message. All right. So as I was saying, now if I plug in this eigenfunction expansion into here, then I can write the time evolution as a so if I am able to find the eigenfunctions of the Hamiltonian, then that allows me, by virtue of this expansion, to solve any general dynamical problem. It's the wave function. Okay. So this is why we want to ask, we want to solve this eigenvalue problem. Okay, and we're going to illustrate some properties of this eigenvalue problem in one dimension today. So explicitly, when this eigenvalue problem is written out explicitly, it looks like this. Okay, so we turn to solving this right now. Alright, so the simplest case of this would be the infinite square well, which you have probably seen somewhere already. Okay, so the infinite square well is characterized by a potential function like this. It's 0 on some finite interval, and we call this 0 to L. Okay, and then it's infinite elsewhere. Okay. So we know that based on the Schrodinger equation, when there's an infinity in the potential, the wave function must vanish at that point in order to avoid having infinities on this side. Okay. So what we can conclude is inside of the potential well, this equation is extremely simple. Okay. It reads so now I can define something called, let's define this to be Kn. Okay. And then, of course, the solution is going to be sinusoidal. So the general solution is going to be a linear combination of the two independent solutions. Now we solve this within the well, we just need to apply boundary conditions. Applying boundary conditions at 0 fixes b to 0, because cosine of 0 is 1, all mathematical. Alright, so boundary condition at x equals to 0 leads to b being set to 0. Okay, and applying the boundary condition at x equals to L leads to the quantization of this Kn, because we know that sine, okay, Knl must be equal to 0. So we get that Kn must be n pi over L. And for now, to make distinct solution, we want the n to run over all of the natural numbers. Because if I plug in a negative integer, you don't get a real you don't get a new solution. You just multiply some solution you already have by minus 1. Okay, that doesn't matter. All right, so that's the infinite square well. Now I want you to imagine expanding the well. Okay, so if I shifted the origin to if I had a well like this, that is slightly shifted. So it's 0 for this interval, minus L over 2L, okay. And the infinite otherwise. The physics shouldn't change. Okay. Maybe some of the expression for some of the eigenfunctions will change because of the changed boundary condition. But this quantization condition is not changed. Okay. So now I can imagine in here, I can imagine taking L to infinity. Okay, now I have an infinitely large square well, okay? But as I'm taking L to infinity, this quantization condition is not changed. Okay? So by doing this, although I can have the Kn, they approach a continuum, they stay countably infinite. Why do we bother with this? Well, later in the course, we're going to be concerned about the number of states. So counting states is easy if they're countably infinite. Okay. Counting states would be impossible if you assume strictly that the problem exists on the real line, and hence there's no way to quantize the Kn, and they can take on any real value. Then you cannot count states. Okay. So it's important to have this picture in your head. Okay. And then when the well is really large, okay, we no longer want to use sinusoids because these just represent standing waves. we might want, for some problems, we might want to use waves that are traveling. Okay, and because the well is infinitely large, locally we don't care about the boundary condition far away.
May I want to explain what you mean by Kn going to a continuum? What does a continuum mean?
Okay, a continuum means that there are so if I draw right now the Kn, they are like a staircase, right? Each increasing by pi over L. All right. So as I take L to infinity, this staircase is going to smooth out. Right? So the value that Kn takes approaches a continuum, but nevertheless, it's still everywhere. At each L point, it's still quantized. Okay. So this is not a continuum like all of the real numbers. So as I was saying, this equation has two other linearly independent solutions, which we can use. We can use the complex exponentials to represent them. So another way to write it is that we can have a forward traveling wave and a backward traveling wave. Okay. Now neither of these by itself will satisfy the boundary condition for a different system. But if you include both of them, you can still make the sign come out. But locally, we don't care about that. And notice here that, remember the quantization condition for Kn says that n belongs to the natural numbers. Okay. But now if I allow n to take on negative values, I can combine these two. Okay. I can combine these two into a single set of eigenfunctions, which is C times. Okay. And then I allow, the quantization condition is not changed, but now I allow n to be any integer.
So n cannot be 0, otherwise it's
And you can still be 0, but you don't really get a solution. Okay. The solution is over here. If you have n equals to 0, that corresponds to
everything will be 0.
everything being 0. Okay. And over here, that's a constant. That is not a legitimate wave function. Okay.
So n cannot be 0. Otherwise,
Can be 0. Yeah. Well, what happens when n is equal to 0? So
there's no.
You have from 0 to L, okay, a constant. It's still normalizable as long as this L is finite. Okay. But it's not a very interesting wave function.
So, I have another question on the boundaries.
Okay.
Because there's a abrupt change on the boundaries.
Okay.
It's about, I don't know whether we have to apply an actual constraint on the boundaries. So
Okay, so if you look at the Schrodinger equation, boundary condition can often be read off. Okay, so if you look at the Schrodinger equation, and suppose that for now we don't have any infinities in the potential. So what you would have is, you could have finite jump to the potential, and that could be offset by the second derivative. So you allow first derivatives to, if you want first derivatives to be continuous. But the second derivative could have finite jumps because I might incorporate some finite jumps into here. But if I allow for infinities, then the only way for this to make sense is for the wave functions to vanish where there's an infinity. Alright. So now, let's turn to the problem of normalizing this function. So as long as we stay on the interval 0 to L or minus L over 2 to L over 2, as long as L is finite, however large, we can normalize this function by, the normalized ones are, okay, you can check this very, very easily. Okay. But now, to approach the free particle limit, you see that we can't safely take the L goes to infinity limit because there's no way to make sense of this function anymore. So that says, to have a legitimate wave function for the free particle, you can have this. But there's a remedy for it. You can make a normalizable wave function by superposing many or a number of these traveling waves with different cadence. I can make a wave packet. Okay. a wave packet is the legitimate solution, a wave function for a free particle. So now we get to the first new thing that quantum mechanics tells us is that there is no such thing as a free particle with a definite Kn. And you must superpose many Kn's in order to approximate a free particle, a wave packet. Right? So there is no such thing as a free particle with a definite momentum. Okay, or a definite energy. Because remember when we defined Kn, it was related to the energy by this relation. Okay, so that's something that you should remember. Quantum mechanics says that there are no free particles with a definite momentum or energy. So now, having investigated the case of a free particle, we can move on to a more interesting potential, which is a piecewise continuous potential. Okay. So piecewise. Okay. So what do I mean by that? We could have okay, some potential like this. Everywhere on this potential, then we have a nearly free particle problem. Okay? But there is a difference, however. So if V is strictly less than E, okay? So I write down the Schrodinger equation for a constant potential. For a constant potential, this amounts to simply subtracting V from E. Okay. There's no essential difference unless the sign of this changes. Okay. When the sign of this changes, this is negative. Okay, if V is greater than E. Then you have negative on both sides, and you know that you no longer have complex exponential. You have real exponential. So to solve that, let's define for the case E is less than V. Okay. First of all, think about what classical mechanics says. Classical mechanics says this is forbidden. The particle cannot exist where its energy is lower than the potential energy. But quantum mechanics says something else. So let's define kappa, okay, to distinguish with K. And let's call it V minus E, so it remains a real number. Okay, so now if we solve this equation for E less than V, we get two independent solutions corresponding to, let me just use A and B. Kappa. Okay, so two solutions. And again, you need boundary conditions to dispose of any one of them. And to make sense of them, you have to remember that wave function needs to remain normalizable. Okay. So if I had a situation like this, which is quite important for electrical engineering, and this is a step potential. Okay. If my wave function, if I have this is the V. Okay. If I have a wave of definite energy V. Okay, I'm saying a wave of definite energy, not a particle. If that's incident on this potential, then what would happen here is you would take only this solution, right? Because if V extends to infinity, then you can only take this solution. This one is not normalized on. So if I draw a diagram, it will look something like this. Okay. This being the x-axis. So the inside of the potential, where classically the particle is forbidden to be, okay, quantum mechanically it can penetrate. It can penetrate it to within the distance of kappa, 1 over kappa, sorry. Okay. So Now, something even more interesting happens when you consider a finite potential barrier. So a finite potential barrier. And still V is here, and I choose for some particles, some waves to have energy less than V. Now, since this is finite, there's always a way to normalize even this solution, okay? Because it only exists within a finite region. And so I need to include both solutions over here. Right? So there's of course, the wave is going to die out, but simultaneously there is a way for it to grow. Okay? And so therefore the wave function extends to the other side of the barrier through this exponentially growing part this time. Okay. So the particle could penetrate this barrier. It's not very likely that it'll penetrate. And later we will learn how to calculate the transmission coefficient here, okay, the transmission probability here. But for now, it's just important to realize that so long as you have a finite barrier, okay, the particle can penetrate. So quantum mechanically, not only does this say a particle can go through barriers which are higher than its energy, it also says that there are no ways to actually trap a particle forever. Okay. So if I did some experiment, okay, and the experiment is only concerned with a particular place, then those particles have a lifetime because there's a chance for them to escape. Okay. Always. All right. And then we get to the using this picture and this piecewise constant potential picture, piecewise continuous potential picture. Sorry, this should be piecewise constant. I don't mean piecewise continuous. Okay. Using this picture, we can distinguish between two types of states. Okay. So by comparing the energy of the particle with the potential energy at plus minus infinity on the x-axis. Okay. Now, if this is less than this, then we know that the particle is bound to within some region, right? Because somewhere we're going to have its wave function decaying to 0, and it doesn't extend anymore. Okay. But if the energy of the particle or wave is higher than any one of these things, then there's no way to look. The particle is actually not localized. Its wave function will be extending everywhere. Okay. All right, I should say the wave is not localized. To make the particle's wave function, you again have to superpose waves. Okay, so we call these bound states. And if E is greater than either of E plus E minus infinity, we will call these a scattering state. Okay. Now these things are equally important. Right now we are going to specialize to bound states because we lack the tool to study scattering states at this moment. The tool will just be the probability current concept, okay, which we will introduce today. All right, so let's consider. So you've already seen the bound state, right? There are bound states for the infinite square well. But now let's consider its variation, which is an extremely useful example, even having a lot of actual applications. So let's talk about the finite symmetric square well. Okay, so let me draw let me write down the potential for you. This is, so I'm going to have the reference of energy at 0. And so then the well is modeled by a negative potential somewhere. Since it's symmetric, I choose to place it in this interval and then otherwise. Okay, so when I draw this, it looks something like this. Okay. So now we're going to consider negative energy states, so that the energy of the particle, say over here, is less than the potential barrier, so we have downstates. Okay. So how do we solve this? Well, we know what happens when the particle is inside here. We've already written when the energy is greater than V, we write down sinusoidals. So we make a guess for the wave function of the particle. On this side, it's going to be exponentially decaying, but we want to choose a normalizable solution because this extends to infinity. Okay. Okay. Now, because I'm going to do some math with both of the k inside and outside, okay, so I want to distinguish it. I'm going to use q. Is that okay? But this has nothing to do with the coordinate we used before. Okay. This is just so that it's clearer. So there's the sinusoidal solutions within the area, within the well. Okay, and then this is valid here. This is valid here, and so on. Alright, so this is, we make a general guess for the solution everywhere. And this guessing the general form of the solution not only solves the finite symmetric well problem, we choose this as an example because it's easy. Now, if I had a piecewise constant potential, then I can use that to solve for any kind of piecewise constant potential. Okay. I just have to match boundary conditions at each discontinuity. Okay. So now the strategy here is we have 4 constants. Right? But that's okay because we have 2 boundaries, and at each boundary we're going to have continuity in the wave function and its first derivative. Okay? So the thing is determined. Okay? So basically we write down these continuity conditions and then specify these. But there's an inherent symmetry in the problem, so that's why it's a symmetric square well. Okay. The way we set up this problem is so that we can take advantage of a symmetry of the potential. Now, in your homework, you're going to have to believe me for now. In your homework, you're going to prove that in 1 dimension, if I have a even potential, then the eigenfunctions are going to be either even or odd. Okay. So we will have either even or odd solutions, and that simplifies the problem a lot, right? If I have the even solutions, that means A and D are equal, right? And then we get rid of the sign, because sign is odd on this side as well, right? Similarly, for odd solutions, okay, A is equal to minus B, and then you get rid of the cosine. Okay, so let's consider even solutions now, and let's apply. So since we've already obtained 2 relations between these 2, we only need 2 more boundary conditions. So let's apply the boundary conditions here to fix the other constants. Let's apply the boundary condition at minus A. Okay. So first of all, continuity in the wave function itself. Okay. Q minus A turns just into QA, right? Because we're inside of a cosine. And then the next thing is continuity in the first derivative of the wave function. On this side, we get a minus sign from doing the derivative. Minus A. So these 2 minus signs actually cancel out. Okay. So now, the easy way to solve this is you have sign here, you have sign here, there's a common factor here. So we divide these 2 equations. Okay. Dividing this, we get a tangent. Right? Tangent of QA is equal to, on this side, you have a kappa here, and then you imagine moving the cube to the other side. So this is the quantization condition, and I call it quantization condition because you'll see later how this quantizes. This is a condition that fixes these constants, okay, for the even solution. Let's do the same thing for the odd solution. And let's still apply boundary condition at minus a. That goes to minus c, right? Okay. And then the continuity of the first derivative becomes. Okay, so we get no minus sign from the. This would be QC cosine. Okay, because if I plug in a, right, cosine b. Even. All right, so now I again divide these two. I also want a tangent. Okay. So let's divide the first one by the second one. And you can see easily that the condition becomes okay for the odd solution. Okay. Now these are transcendental, so we need to solve them graphically. And the graphical, solving it graphically actually corresponds to some very nice physical meanings about the size of the potential well and how many bound states there are. Okay. So let's do the even one first. Even. Okay. The condition is that this is equal to kappa over 2. So remember, oh, I forgot to write down important over here, the kappa and q are already determined, right, based on these parameters. So we can write kappa is equal to, we have said these are negative energy solutions. So remember this absolute value here. Okay? And then the q is equal to okay. I can easily make sense of these expressions. Now I'm going to do some algebraic manipulations which are not that important. So let me call this QA something called the C.
Then why don't you explain why you put the magnitude over the E?
Oh, okay. Because we have the way we've written down these solutions, right? K and Q are both real numbers. So we want to take but E and V naught and minus V naught are both negative. So the difference between the energy, which determines the Q here, is V naught minus the magnitude.
You have erased the formula for K or Q from the blackboard. Why didn't you write down the original form?
Okay, the original form.
The uncorrupted form.
The uncorrupted form is K is equal to 2m E minus B divided by h bar squared. And this K corresponds to the complex exponential. Or this. Okay. So when you want to use the real one, this would be complex. Okay, so to take care of that, we just switch these signs. Switch up.
Isn't that the 0 point at the intersection?
Oh yeah, the 0 object is here.
In that case, shouldn't 0 minus absolute E be negative for this one?
But I have to find minus.
Oh, okay.
Yeah.
That is just
Remember remember this.
all right.
Okay. So I define a quantity called this, and then let's see what. To get rid of the square roots, let's see what is squared. Now this is just kappa A squared. Alright. So now this term is interesting. It only depends on parameters of the well. The strength of the well and the width of the well. Okay. So I'm going to call this something called beta squared. Okay. So now we get that the C squared plus kappa squared alpha squared is equal to beta squared. Right? So now if I divide through, I want K over Q. So if I divide through by C, I get 1 plus kappa over Q squared is equal to beta squared over 2C squared. Okay. So you see that kappa over Q.
Make your kappa different from K.
Yeah.
K and kappa look the
Right.
same.
Right. That's why I don't want to use kappa and K. So even if they look the same, you still know which one is which. Kappa over Q is equal to the square root of beta squared C squared minus 1. Right? So now, if I plug in this condition, this is just C here. Right? So this is equal to tangent of the C. Did I make a mistake anyway? Yeah, then this one's right. Yeah. Okay. So now we solve it graphically, but it's not very easy to graph this function. So what we can do is, if you are having difficulty, you could always make this into a function f, and then just invert this function and see what it looks like.